Okay. So here we have this complicated truth table. Turns out that this thing is called a tautology. I like put little letters that represent each one of those if and only if statements. But what do you think it's called if we would have gotten a proposition where all of the values were false? Oh, right. It's actually called a contradiction, okay? If it can't ever be true, we call that a contradiction. Okay, so there was a hand up here in the back. What did you have something to ask, sir?
Yes. So for the A plus B thing, just from the P to Q or the not P to Q, just one of those sides has to be true for the last statement to be true.
Are you talking about the if and only if, the biconditional, or are you talking about the last column?
So for the last column, only either A or B has to be true for it to be true.
Yes, if they were both false, it would be false. And if they were both true, it would be false. For the exclusive or, what you're saying is, look, you either do this or you do that, but not both, right? Okay, that's what would have to happen in order for it to be true. Okay? Are we good to go on that? All right, so here's the next little puzzle for you to work on. I already talked about how I love logic puzzles. Okay, so here you go. Think about this little logic puzzle with your neighbor. There is a famous mathematician. I would be remiss to not mention him in here. His name is Smulyan, Raymond Smulyan. A very famous logician. He is known for creating amazing logic puzzles. There's also another guy named Martin Gardner that used to make logic puzzles. And he actually made the knight and knave and whites and pinks. And I mean, he has all these logic puzzles that involve those sorts of things. Okay? So think about this one with your neighbor and let me know what you think. Think about it with your neighbor and see if you can come up with a rationale here. Okay, so talk with your neighbor for a minute. What are the 4 situations that we could have? Yeah, Monique.
They're both knights.
Okay.
Both knaves. A is a knight, B is a knave, or A is a knave, B is a knight.
Right. So they're either both knights, both knaves. A is a knight, B is a knave. A is a knave, B is a knight. And in theory, those phrases that are uttered should only be compatible with one of those situations. Okay? Sometimes these logic puzzles will have some weird subtlety that you'll have to be like, all right, yeah, it was a Tuesday or something, okay? But in this case, I don't think that's going to happen at all. So can someone talk us through which of those it has to be? Yeah.
Is true, then B saying that A is a knave is a lie, which renders the first statement false. So then I assume that B is a knave, saying A is a knave, which renders A's statement false, rendering B's statement true.
Okay, so which one is, okay, so for instance, okay, let's start with, I mean, I see where you're going. So let's suppose that A was a knight. Okay? If A was a knight, he would be telling the truth. Okay, and if he's telling the truth, that means B would have to be a knight, and so he would also have to tell the truth, which he doesn't. Make sense? So could A be a knight? No. So A must be a knave. Okay? And if A is a knave, then what? Now talk us through it. So A has to be a knave. Now what? Yes, right here. Yeah.
Then if A is a knave, he's telling the truth. He claims that A is a knave, so he must be a knight.
That's right. So we know A is a knave. B says A is a knave, which is the truth. Therefore, B is a knight. So A is a knave, B is a knight. Yes. Okay, so you see how that kind of goes here. Sort of a quick and dirty way to do it also would be to like just assume each one of those 4 cases and find something contradictory in the other ones or whatever. But we kind of reasoned that out there. What we did is we kind of started by assuming something, namely, well, what if A was a knight? And then we saw that we got into trouble. Therefore, A has to be a knave, right? And then we kind of went from there. Okay? There's another logic puzzle in here that I would, oops, where is it? Oh, I know where it is. I hit it, but it's in the slideshow, okay? It's a little bit trickier, but if you go onto the course webpage, I'm posting these slides, right? Go on to the course webpage. That's a little exercise for you to think through it. It chucks, right? It's another little logic puzzle. Interestingly, in this case, A says, okay, at least one of us is a knave, and B says jack squat, okay? So what's going on there? So I would challenge you to kind of think about that, okay? It's a good one. I love logic puzzles, okay? I hope you do too. Okay, any questions on that before we move on? All right, I want to talk about equivalence a little bit. We've talked about equivalence, like logical equivalence, informally, but I want to talk about it more formally. And I also want to draw your attention to certain kinds of equivalences that I want you to just be able to know, okay? So propositional equivalence. Okay, so first of all, some terminology. I already brought this up. A tautology is a proposition which is always true. Didn't we just see an example of that in the example that started the class? Yes? That was a tautology. Here's another example of a tautology. P or not P. Okay? That will always be true. Yeah? That's like me saying I'm left-handed or I'm right-handed. Yeah? And one of those two things is going to be true. I mean, so technically, I guess you could be both. You could be ambidextrous, but this is not the exclusive or case anyways. Okay, or you could say, I'm going to eat a peanut butter sandwich for lunch, or I'm not going to eat a peanut butter sandwich for lunch. Both, that will always be a true statement, right? Silly. But tautologies are important because they identify valid argumentative forms. So we'll see that later on, all right? A contradiction is a proposition that's always false. And now I'm saying example. Yes.
I will eat fish and I won't eat fish.
Yes. So what is the symbolic form of that? That's an example, but there's a general symbolic form to that that we could write down here. P and what? P and not P, right? It's silly. You know, if P is true, then not P is false. And of course, in an and, you need them both to be true for it to be true. Yeah? A contingency is any other proposition, a proposition that is, you know, whose truth value is contingent upon the truth values of the things involved. Yes? Okay, so that's a nice little term to think about. Okay, so let's talk about logical equivalence. What makes two compound propositions P and Q equivalent? I'm just talking about, I'm talking about at the kind of baseline symbolic level, not necessarily intuition, but at the baseline symbolic level, how can we tell if two propositions are equivalent? Yes. So truth tables have to behave exactly the same, no matter what the values of the propositions that make them up. Yes? So the answer to that is the same truth table values. Okay, same truth table values. Those will be equivalent propositions. Okay? I've already kind of shown you some notation for equivalent propositions. like the triple equal sign, right? And we'll see that kind of make an appearance here pretty soon. Okay. Okay, same truth table value, like I just said. What does that mean about P if and only if Q? So suppose P and Q are equivalent. Okay, so P is equivalent to Q. And by the way, I'm letting P stand in for maybe a perhaps really complicated statement, kind of like what I did with capital A and capital B earlier. Remember that? So P could potentially be some really complicated, like, proposition that consists of all sorts of logical connectives and propositions inside of it. But I'm assuming that P is equivalent to Q. What does that mean about P if and only if Q? If P and Q always have the same truth table values, what does that mean about P if and only if Q? Yes. It will be a tautology. Yes? Because it will be true if and only if true, which is true, or it will be false if and only if false, which is also true. Okay? So this thing would be a tautology. Okay? That would be a tautology if P and Q are logically equivalent. Okay? And a lot of times, it's helpful to have this truth table thing in our back pocket as a way of detecting logical equivalence, because it's not always obvious intuitively why two things are logically equivalent. But oftentimes, once you see that they are at the level of truth table values, you then can say, oh, why are these logically equivalent intuitively? And then suddenly it'll be like, oh, I see what's happening. And you can kind of reason out what's going on. Okay? All right. So you write it as P triple equals Q. That means logically equivalent to Q. By the way, if you're in a definition, so I mean, we're trying to be really logically precise here. Notice I said if right there. You know what I mean? So I said definition, P and Q are logically equivalent if P if and only if Q is a tautology, which automatically amounts to the truth table values all being the same, yes, for P and Q. But I said if there. I didn't say if and only if, but when you're in a definition, if automatically means if and only if, okay? So definitionally speaking, when you're saying, here's my definition, and you use the word if, this, then that really means if and only if. So P and Q are logically equivalent if and only if P, if and only if P, if and only if Q is a tautology, right? We're saying if and only if lots of times here, okay? Okay, any questions so far? Questions?
So does the idea of logical equivalence apply only to compound propositions?
Typically, no. I mean, I could have something like this, John. I could have, I mean, this is sort of stupid, but watch. I could say P, and then I could have P again, right? So T, T, F, F, and T, T, F, F, right? And you could say, hey, look, P is equivalent to P. Know what I'm saying? I mean, like, in that even, that's not interesting, but it doesn't necessarily have to be a compound proposition, but it's only really interesting in that case. Does that make sense? Okay. Ah, good old De Morgan. Nice picture of him right there. Okay. De Morgan's law says that if I negate an and, okay, that's what that first line says. If I negate an and, or right, if we want to be really clever logicians, we would say we negate a conjunction, then it's the same thing as the disjunct of the negations. Okay, that's some pretty fancy, that's fancy speak. Or look, if I negate an and, it's like the or of the negations. Yes? So think about this for a second logically. What if I said, I am going to eat a sandwich and a salad for lunch? Right? I'm going to eat a sandwich and a salad for lunch. Okay? What would be the logical negation of that? What would be the opposite of that? Okay? I'm not going to eat a sandwich, or I'm not going to eat a salad, right? So that, like, I would have not followed my own promise if I failed to do either one of those. Yes? And by the way, how could I check to make sure? So do you see the intuition, at least, before we even get into it? That's intuitively what's happening. You guys kind of, you have an automatic feel for why this makes sense. But let's at least kind of make a little truth table here. Okay, here's P, here's Q. We're going to go true, true, false, false. Okay, true, false, true, false. Okay. Of course, P and Q, we know what that is, right? So that's going to be true, false, false, false. Interesting. And what about the negation of P and Q? Well, the negation of P and Q is false, true, true, true. Okay, and now I'm going to put not P and not Q. Okay, I know I'm kind of writing over some things here, but I think you'll forgive me for that. Okay, so false, false, true, true. And what do I have? False, true, false, true. Okay, what if I take the or of not P, so not P or not Q? So check it out. Not P or not Q. False or false is false. False or true? True, true or false? True. True or true? True. And we see it. All right, look at this. False, true, true, true. False, true, true, true. Right, they have the exact same truth table values. Therefore, they are logically equivalent. Yeah, but we also saw that on the level of intuition. That's a good thing here. What does this kind of remind you of? Maybe something from algebra, perhaps? Kind of looks like we're almost like distributing something through here, right? But the and, like the thing is, you sort of are distributing this negation, but the negation negates not just each of the individual propositions, but it also negates the connective, right? The and, okay? In each one of these cases, you see the negation, it flips the propositions, but it also flips the and to an or. And it does the exact same thing in the case of the or. Not P or Q is equivalent to not P and not Q, okay? So think about that. What if I said, I'm going to eat a sandwich or a salad for lunch? That was my verbal promise to you. I'm going to eat a sandwich or a salad for lunch. What would be the logical opposite of that? Well, I don't eat a sandwich and I don't eat a salad, yes? Like I failed to do both of those things, okay? So we can even see at the level of intuition what's going on there. By the way, I wrote those things up there, but of course we have the things sitting right there, you know what I'm saying? So there's a little truth table right there, okay? So Morgan's law makes sense. By the way, this will come up again in the context of sets and Venn diagrams later on. You've probably seen a Venn diagram at some point. The reason I'm giving you the logical foundation, because we're going to talk about sets eventually, we're going to use these logical symbolic tools to really understand sets well. And there's something called De Morgan's law in set theory as well that's really rooted in the logic we're talking about right here. Okay? By the way, what do you think would happen if I did not P and Q and R? What do you think would happen? Same sort of thing. You would negate each one of these and the ands would change to ors. Not P or not Q or not R, etc. Yes? And a similar thing would happen in the case of a disjunct, an or statement. Okay? All right. Moving on. Rewrite the statement, I will not order bacon and eggs. Okay, so I mean here, let's just kind of do this together. I will not order bacon and eggs. So not B and E, yeah? So what's that equivalent to? I will not order bacon or not order eggs. Does that make sense? Okay. Okay, it's a quick application of the De Morgan law. Very important, very important. By the way, I used to work at another institution, and one time I created a piece of curriculum that needed to be implemented in the registrar's system. Okay, and in the registrar's system, it was going to have to check whether someone was a math education major or a math major or was a middle childhood math specialist or something, right? They were specializing in middle childhood math or something, okay? And the registrar told me, that's impossible to check those things. And I said, what? And she said, no, it literally, you can't do it. Like it can only handle and statements. And I said, can you negate things? And she goes, well, yeah, of course. And I said, De Morgan, it made no sense to me that the system at a university would not be able to handle the two types of logical statements, ands and ors. And indeed, it could handle ors, but you had to use the De Morgan law. Does that make sense? That's a practical application of the De Morgan law in real life, right there, okay? So constructing new logical equivalences, sometimes to show that two things are logically equivalent, you can use things like De Morgan's law and other things that you know are logically equivalent to work your way from one side to the other so that you don't have to like go through the rigmarole of actually writing out the truth table values. Sometimes you can manipulate these things kind of like you would an algebraic equation, yeah? You say this equals that, equals that, equals that. You can do that with logical statements as well. Just using some things that you know to be true, okay? So you just kind of write this chain of logical equivalence symbols and work your way from A to B, okay? Here are some key logical equivalences that some of them, I mean, there's names here. I'm not necessarily wanting you to memorize these, but I just wanted to put the names there so that you have them, and you're aware of them. So the identity laws, okay, by the way, if you end up taking digital logic design, they will use slightly different notation. They'll use zeros and ones because they're a bunch of computer science people, right? But 0 is false, 1 is true. And they'll also, instead of using the and symbol we do, they'll actually use times. They'll actually use the multiplication symbol. And for or, they'll actually use plus. Does that make sense? They'll actually use plus. And a lot of the manipulations they'll do in kind of this binary arithmetic. And that works. And actually, the first law right here makes sense why they would choose to do that. Look, if you go P and true, then do I really care about the true anymore? What's going to be the determiner of the truth of that statement? P. Does that make sense? So really, I can reduce that to just P. So doesn't that look like I kind of multiplied by 1? Does that make sense? That's why it's called the identity law. It's almost like multiplying something by 1. Now, what do you think that second one is right there? P or false is equivalent to P. What does that remind you of doing? Like adding 0 to something. That's why those DLD people choose to represent an or with a plus, false with 0, and an and with a times, and true with 1. Okay? And they kind of treat things in this binary arithmetic. But doesn't it make sense to you that if if I have P or false, then the truth value of that or statement is completely determined by P. So that would be equivalent to P. Domination laws. Ooh, that's that's interesting. Domination laws. If I take P or true, do I even care what P is? No, it's true. Yeah. What about P and false? False. What does that remind you of? Think about it. That's kind of like, adding 1 in the first case, right? And the second case almost like multiplying by 0, which just kind of kills it. Does that make sense? Okay. The idempotent laws. So P or P, are you serious? I might as well just be working with P. P and P? P. Okay, double negation law. By the way, all of these are easily verifiable in a truth table, but we can kind of see why they would have to be true. If I negate a negation, guess where I am back to? The original thing. It's kind of like a negative negative. Does that make sense? Okay. Couple of negation laws, P or not P. We already talked about that. That's actually a tautology, isn't it? That's always true. P and not P, that's equivalent to false. That's a contradiction. Okay. Questions on that? These are just kind of some basic logical equivalences that you can take to the bank and that you can use if you're in the process of manipulating something. Some other obvious things. P or Q. I mean, seriously, that's the same as Q or P. Okay, honestly, we know that, yes? P and P, that's equivalent to Q and P. Or P and Q, same as Q and P. There's associative laws. Namely, if I have a triple and, or if I have three things that I'm doing an and with, then I have to decide whether to do the first two or the second two. And what this is saying is it doesn't matter, like whether you do the first two or the second two. Does this remind you of like when you're multiplying numbers together, it doesn't matter. Like if I do 2 times 3 times 4, you have to make a decision whether to do 2 times 3 first or 3 times 4 first. Does that make sense? But it doesn't end up mattering whether you do it one way or the other. That's what the associative laws of conjunctions and disjunctions work exactly the same in logic. Okay? Oops, I think I have some stray parentheses right there, but look, there's a distributive law. Basically, you can distribute an or over an and. Okay? So P or distributed to Q and R, I can basically distribute that. That kind of reminds you of multiplication distributed over addition or something like that, right? Or the other way around. So P or Q and P or R. Look, I have some stray parentheses on the left right there, and there's a stray one next to the and right there. But you can see that you distributed the or over the and. That one's a little trickier to see. It would behoove you to actually go in and look at a truth table to sort out why that's the case. Monique, did you have your hand up? Same thing for the second one. I can distribute an and over an or. Do you see that? It's like basically P and parentheses Q or R. You distribute through, and that's the same as P and Q or P and R. Right? So the P and can kind of distribute through across the or. Okay? You can also think about intuitively why that happens to be the case by thinking about your favorite lunch example or something. Absorption laws. So think about this absorption law. P or, parentheses, P and Q. The easiest way to see why that's true is to actually distribute that or over that and. Actually, I think, hang on a second. Is that just equivalent to P? Let's see here. Yeah, maybe it is. So if P is, so think about it for a second. If P is true, what's automatically going to be the case about that or? True. What if P is false? Automatically false. Therefore, that thing on the left has the exact same truth value as P itself. So yes, that is what I meant to write. Yeah? What about P and P or Q? Well, if P is true, the or is true, yes, and therefore the and is true. So it's the same as P. What if P is false? We're done. One of the things on the and is false, and therefore the whole thing is false. Does that make sense? Okay. Next time we'll come in together, or actually after Friday, we'll do the Euclid proof of the Pythagorean theorem. But we'll come in and we'll start manipulating some stuff. It'll be a great time.